Let's begin. I hope you gave me some good book suggestions. We'll see. Will be for the TAs as well. So they've been wanting to read a lot recently, and they come and tell me, what should we read? Oh, Professor Saab's like, I don't know, go read the internet or something. And so, I hope we get some good book suggestions. I personally love Russian literature, like classics, Tolstoy, Dostoevsky on classics, but that's kind of where I'm stuck. I don't think anything new has had such impact, but who knows? There's so many books out there, so I'd be interested, fiction and nonfiction. Okay, so I'm guessing most of you finished with the quiz. Polyfit, only for full polynomial models. Curve fit for anything. Polynomial, linear, nonlinear, whatever. So polyfit only for full polynomial models, which means for regression, linear regression type analysis. Before I finish, we're done with regression, but I still have this lingering thing that I mentioned last time. I'd like to do an example with you, because this will be on your homework assignment, and this is a very practical thing you will see, and that's the linearization of a nonlinear model. And there are about 3 types you will find in modeling, a few types that you can take in a model that would otherwise have resulted in nonlinear normal equations. You do a transformation on it and make the model linear in a regression analysis sense, so the normal equations become linear. And I gave this example of this type of model, alpha e to the beta times f of x, and the parameters are alpha and beta. Those are the coefficients that we would like to fit so that our model minimizes the error between observational data and its output. And then I said, if you take the logarithm of this model and you just simply rename the natural log of this, and you simply rename the log y, call it the new y data. So you remember you have y data. You take its logarithm, now you have new y data. And log alpha, just call it a naught, constant, plus beta, which is a constant, times f of x. So that will become your new regression model. And that is a regression to a straight line, which results in linear normal equations. And then you can go back, once you solve for a naught and a1, you can extract alpha and beta and then put them in the original form, and you'll be good to go. A classic example of this is reaction rates in kinetics. And the classic Arrhenius model for the reaction rate is you have a rate constant, k, as a function of activation energy and temperature and gas constant, etc. So it looks like some coefficient a, which we call the pre-exponential factor, times the exponential of minus this EA over RT. Now, EA is the activation energy. You need a certain threshold of energy in the system before you can make a reaction occur. Okay? So just combining 2 reactants together they're not going to react. They have to have the right temperature, because there's a barrier before they can react. And that barrier is the activation energy. You need enough energy in the system to activate the reaction so that the molecules can start kind of communicating with each other and exchanging. Over RT, R is the gas constant, just standard constant number, that's the universal gas constant, times T, which is the temperature in Kelvin. Okay. Now, in these cases, we don't know A or the activation energy for a certain mechanism. So in this case, benzene, diazonium chloride, and chlorobenzene, if it reacts to chlorobenzene and N2, and you go and measure this. You don't know what the activation energy is. You don't know what the pre-exponential factor is, but you can go and measure the reaction rate versus temperature. So at different temperatures, you can measure a different reaction rate. And here we have like 1, 2, 3, 4, 5 data points. Okay? And our objective is to find A and the activation energy. So if I take the logarithm, so this is in the form alpha e to the beta times f of x. In this case, x, the independent variable, is the temperature. Alpha is A, beta is EA, and f of x is minus 1 over RT. Okay? So once you take the natural log of this, you convert it into this form. And if you plot the data of log k versus minus 1 over RT, then this is what you get, indeed a straight line. And so the model does look like in the log space, it would be good to do a regression to a straight line. And you just say, okay, this is of the form A0 plus A1x or C0 plus C1x, whatever, and then you can do your regression this way. All right, so let's go ahead and do this in Python using polyfit. All right, it's going to be very simple. So open up a Jupyter notebook. We'll put in the data together and try to find the solution. So we'll have to do this from scratch for everyone in the back. And you can just copy your boilerplate stuff. From NumPy, we definitely need NumPy. I like bring in the magic and matplotlib. And let's put in our input data. I'm going to call them xi and yi as usual. So the original xi, the original data, and because I'm going to transform it by taking the log and stuff, I'm going to call it xi underscore. Because the transformed one, I'm going to end up calling it xi. So in anticipation of that, I'm going to put an underscore here, because this is going to be temporary, mp.array, and we have what? Where is the slide? I'm going to move to Creston. Okay, let's see, 3, 13, 19, 23, 28, 33. 13, 19, 23, 28, 33. Okay. Okay, 323, 328. Yes, I've been doing some memory exercises given the senior moments I had last Tuesday. Been listening to more music and singing. Apparently it helps. Why nobody laughs at my jokes this year? It's like, am I that out of date? It's okay to laugh. You're not going to offend me. I'm not seeing you anyway, so. Okay. So let's see with the, oh, this one is going to be a little bit annoying. Okay, so let me see if I can copy those. Okay, this is easier. Yeah, sorry, you have to type all of those while I just copied them from the slides. Okay, so this is the, now you may want to name them TI and KI, I understand. I just want to do XI and YI to keep in my mind this is independent and dependent, but it's okay, these are temperatures. So temperatures and reaction constants. Okay. Give you a second to do that. Did anyone come up with a nice slogan for, you know, when we have data? Aaron, everybody's pointing at you. Do you have like something? Daxton, come on. I love it. When data is spotted, it better be plotted. Okay. Okay. Thank you. Okay. So when data is spotted, it better be plotted. I like that. It's a good one. Even ChatGPT didn't match that. So I asked ChatGPT, give me some fun ideas. Okay. So when data is spotted, it better be plotted. Now, is there a word, plotted? Yeah, there's a word, plotted. Okay, okay. Aaron. Okay. All right. Aaron. I don't know if you've seen that clip on YouTube about the names. Okay. Let's plot it. So plt.plot xi underscore yi underscore, and we'll put the symbol. And look at that. It does indeed look exponential in nature. So that's why the proposed model is exponential, a e to the minus ea over rt, okay? So it does make sense, right? Now, you could do interpolation with this data if you want, because it looks kind of like a one-to-one. There's not this scattered like human data and other observations. But again, the power of a regression model gives you a formula that you can use and just give away, and you don't have to give the data. And with interpolation, you always need the data with you. With a formula, you just take the formula and start applying it to make predictions. So that's the advantage of regression. Okay. Now, I want to transform this. If I were to do the fit directly on a e to the minus ea over rt, we would have to use curve fit directly, because this is a nonlinear. This is a model that will result in nonlinear regression. Agreed? So you do curve fit like we did last time. You give it the model form. You just plug it in. It would return a and exponential activation energy, and you can work with that. But if you want to transform it, there's a couple of steps. You need to first transform the data into log space. So we need to turn everything into this new capital Y and this new capital X. Okay, so our new data is going to be yi is going to be np dot log of the original yi, and xi, the new independent data, is -1 over r over xi. Agreed? So my new x, I'm going to take -1 over rt and going to call that x, and log k, I'm going to call it y. In my code, k, the original k data are lowercase yi underscore, and the original t data are in the xi underscore. And we need the gas constant, 8.314. Okay. Now I can plot this, plt dot plot. So what I've done, I first transformed the observational data into log space, and then I'm going to fit a line into that transformed log space. So you can think of it this way. Okay? So if we plot now the new xi and yi, and indeed the new transformed data does fit on a straight line. Okay? It does fit on a straight line. So if I were to give you these data, you would say, oh, data, a straight line, regression to a straight line would be perfect for this. Agreed? But that's kind of what we did here. We started with data that looked exponential. We took its logarithm, and we split it in a smart way, and it gave us what looks like straight line. Now, we can simply regress this new data using polyfit. So coefs is equal np dot polyfit. Oh, come on. P dot polyfit. Okay. I'm going to give it the new transformed data xi, yi, and degree equal 1 because I'm regressing to a straight line. Okay. To a straight line. And it should return two quantities. So print coefs. It should return two numbers. What is contained in the first one and what's contained in the second one? So the first number is going to be log a, the equivalent of log a, or this intercept. And the second one is going to be the slope, c1. Okay? So if I define my linear model for the regression, it's going to take some x value and c1 and c0. So sorry, yeah. So the polyfit is going to return the coefficients in reverse order, right? So where is it? It also returns. Where does it return? Just to double check. Parameters, degree, returns. Yep. So the polynomial coefficients with the highest power first. So it returns C1 first and then C0. Okay? So don't forget that in polyfit. So coefs, this would be C1 and this would be C0 in this formula here. So the first entry is C1 and then C0. Okay? So now I'm going to define my linear model with taking C1 first and then C0, and then I will return C1 times X plus C0. I'm just trying to plot it now on top of the original data to see if it does a good fit. So plt.plot the transformed data, okay, xi, yi, and give it a scatter, and plt.plot. Because this is a straight line, I don't need to create a new new data points in between. I can just pick the original ones. Okay, I don't need to do a lin space for this. Now remember our little trick: linear model, xi, and then star coefs, so that I don't have to split the coefficients into C1 and C0. Star coefs automatically splits this into C1 and C0 for me. And if I plot this, this is what I get. Okay? So this is our regressed line on the transformed data. Okay, great, good. There's one more step. We need to go back to the original model, because that's the model you would be selling, you'd be giving away. The exponential, the one that would have resulted in nonlinear regression. Okay? And so simply, if we go back to our math, we know that C1 is EA, so we have the activation energy. But C0 is log of capital A, this pre-exponential factor. So A would be the exponential of C0. Okay? So now let's go back to the original model. Let's go back to the original exponential model. We know that EA is going to be coefs 0, right? Because EA is C1, and C1 is the first entry in coefs. And A is going to be np.exponential of coefs 1. So coefs 1 contains C0. Log A is equal to C0, and therefore A is exponential of C0. Okay? And now we can plot these values with the original data. Okay? With the original data. So define exponential model. Say it takes some t values, and then it has a pre-exponential factor and an activation energy. And this would be return A times np.exponential minus EA over R over T. Okay? So now we can plot with respect to the original data, plt.plot. Our original data was xi underscore and yi underscore, and it put it in a scatter. In this case, I need to do a lin space because this is an exponential curve. To capture the curvature, I need a lot of points between all the min and max value that I have. So we create a lin space. T nu is mp.lin space, going from minimum of xi to the maximum of xi. So the original temperatures, and I want to put 100 points. And finally, we can plot the the exponential model with T nu on the x-axis, and we say exponential model T nu, and we need to pass it A and EA. Agreed? Okay, so let's see how that looks. Look at that. Okay, I know you're still typing, sorry, so I can switch back. Where you want me to go up, further up? Is good here. So all that switching, going back and forth, don't lose track of it. Just remember what you're doing, what your primary objectives are. We wanted to fit the exponential model. We took a detour to transform it to a model suitable for linear regression analysis because it's easier, it's simpler, no nonlinear solvers, no initial guesses and whatnot. And then once you figure that out, you convert your solution back into the coefficients of the original nonlinear model. Okay? Now, it would be interesting to ask the question, is the R squared of the linearized model and subsequently once we convert back to nonlinear space, so is the R squared of this guy equal to the R squared of the original nonlinear model if we were to do a curve fit? Usually it's not. Because with the linearization, you lose some information, and then converting back, you lose more information. So generally, it's a little price to pay, though. The difference is not going to be significant. It is an insignificant difference, but it's not going to be exactly equal. Okay, so the R squared of this guy is not going to be equal to the R squared if you were to do curve fit on the original nonlinear model. Because this guy came from the linearized model. Okay? So there's going to be a slight difference. I think I asked you about that in the homework assignment to compare, do a curve fit, do a linearization, and then compare the two. Okay? Hopefully I don't lose my recording today, but thankfully I have like lectures going back for years, so I can always point to that. Okay. Now this is a more general, there are a couple other models you can linearize. This one, a general exponentiation model. You could do the same with a log form or something like this. You'll see this in your homework assignment, how to do that. And I give you a few hints in the homework assignment. It shouldn't be that hard, but just make sure that, okay, you've converted this here into this form. You also need to convert the observational data. You can't work this linearized version on the original y and x. No, you have to convert those as well. So then you operate in transformed space, you do your regression, and then go back. All right? Okay, I don't think we can afford a 5-minute break. I would like to finish. We're going to be probably half a lecture behind or one lecture behind. It's those quizzes, those darn quizzes. Okay, where's my cursor? Okay. All right, so with that, we conclude regression. It will be on your exam 2, along with interpolation. So that entire section on curve fitting